Dear students, welcome back to the lecture series on solid state. In this module, we will have a detailed discussion on the internal structure of crystals. We will see what is meant by a unit cell, space lattice, and what are Miller indices. In the introductory class, we have seen that a crystalline solid is characterized by a regular, repeating, three-dimensional arrangement of its structural units in a definite geometrical pattern. Or in other words, we can say that crystals are composed of a periodic array of structural units. And what is meant by a periodic array? In this figure, you can see that the two types of atoms represented in purple and green color are arranged in a regular repeating pattern. If we select these two atoms followed by this, okay. So, you can see that if I select this one, the surroundings around this particular unit is the same everywhere. And if you select this one, then also the surroundings is exactly the same as before. So, likewise, if you see this in any particular direction, if you take in this direction or you take in this direction, you can see a definite geometrical pattern which is regular and repeating, and that is a characteristic property of a crystalline solid. So, we say crystals are composed of a periodic array of structural units. And what are those structural units? It can be atoms, it can be ions, or it can also be molecules. Okay. Now, these structural units are also known as motifs. The other name for motifs is bases. So, structural units which can be atoms, ions or molecules can be also called as motifs or bases. Now, on the figure, you can see another term called lattice. So, in the previous class, when we discussed about crystal planes, I also mentioned about the lattice plane. Okay, crystal planes are also known as lattice planes. So, now let us see what is meant by a lattice. Lattice is actually a mathematical concept that denotes a periodic array of points. Okay. So, as you can see in this figure, there are a set of points shown here, and these points are arranged in a particular pattern. Okay. So, these points can be called as lattice points. Lattice points. Okay. So, lattice points are the points which are arranged in a particular geometrical pattern. Okay. Now, what is the relation between a basis and a lattice point? The basis, as I said earlier, it is a motif or the structural units. So, say if the structural unit is an atom. So, if we place each atom on these points, okay, I am going to place the atoms in each of these points. So, what happens? The basis is occupying each of the lattice points. So, when each of the lattice point is replaced by any of the structural units, that is whether it is replaced by atoms or ions, then we will get the three-dimensional crystal structure. So, in this figure you can see the colored structural units or motifs or bases, and each of these bases occupy each of these points in that particular pattern. So, this results in a three-dimensional array of lattice points being replaced by this bases or motifs. So, that generates a crystal structure. Okay. So, hope you have got an idea of the periodic arrangement of the structural units. Now, on the figure you can see, on figure A it is a motif or a structural unit. On figure B you can see the lattice points, and as I mentioned earlier, when each of the motif occupy each of the lattice point, as you can see in figure C. Okay. So, at each point you can see each of the motifs occupying. So, this results in a three-dimensional structure, crystal structure, or three-dimensional lattice, and that is called a space lattice. The lattice points may not be in this particular pattern. It can be any type of patterns. For example, it can be like this. Okay, so this is another pattern of lattice or a periodic array of lattice points. Okay. So, in whatever pattern it is, if such lattice points are replaced by the constituent particles or the motifs, we get a crystalline lattice or a three-dimensional arrangement, which is called the space lattice. Okay. So, what is exactly a space lattice? As I mentioned earlier, it is a periodic array of identical points showing how the constituent particles of a crystal are arranged in different sites, and these sites are called lattice points, different sites in three-dimensional space. Okay. So, on the screen you can see the crystal lattice, which is also called the space lattice. So, you can see red and blue colored atoms occupying the lattice points. Okay. So, a regular repeating arrangement of these lattice points will generate a space lattice, and each point representing the position of a motif. And what is motif? It is a basis or a structural unit inside a space lattice has exactly the same environment as any other similar point. Okay. In the previous slides showed you, that is, if you take this particular point, it has exactly the same environment as we take any other point on this lattice. So, an important characteristic feature of a space lattice is that the position of any structural unit inside a space lattice should have exactly the same environment as any other similar point. Now, on the figure, on the right hand side, we can see the space lattice. Okay. Now, this space lattice may be treated as a combination of 4 cubes. Okay. As you can see, if you take this colored part, so this is one cube, So, this is the second cube, now this is the fourth one, this is the third one, and this is the fourth one. Okay. So, this space lattice is formed by a combination of 4 such cubes. Now, if you take one cube from this, okay, for example, this green colored portion, if you take one cube from this, so that is represented here, and this particular cube, you can see that it is the exact replica of the other 3 cubes. So, this cube is maybe called as unit cell. So, what is unit cell? It is the smallest fundamental repeating unit of a space lattice from which the entire crystal may be built up by purely translational displacements, okay, and that is called a unit cell. Or in other words, we can say that a unit cell is a basic building block from which the entire crystal lattice may be generated, or the entire space lattice may be generated. Okay. Now, what is the characteristic feature of a unit cell? A unit cell has the overall symmetry as that of the crystal. Okay. That is, the symmetry of the crystal as a whole will be equal to the symmetry of the unit cell. Simple words, we can say that a unit cell forms the smallest representative unit of the crystal. Okay. So, do not get confused between a space lattice and a unit cell. A space lattice is a periodic array of the constant particles, and these constant particles are placed in the lattice points so that it will generate a 3-dimensional crystal structure. So, that is a space lattice. And what is the peculiarity of a space lattice? Each point representing the position of a particle inside a space lattice will have exactly the same environment as any other similar point. Okay. Now, what is unit cell? Unit cell is the smallest representative unit of the crystal. From that unit cell, you can generate the entire 3-dimensional crystal structure. Okay. The smallest fundamental repeating unit of a space lattice from which the entire crystal may be built up by purely translational displacements or translational periodicity is called a unit cell, and that is the basic building block of a crystal. And the symmetry of the unit cell will be the symmetry of the entire crystal. Now, let us see what is meant by lattice parameters. So, consider a unit plane. In the previous class, we have seen what is meant by a unit plane. It is also known as a standard plane, which is chosen in such a way that the plane cuts all the 3 crystallographic axes. So, consider a unit plane ABC. We have the 3 crystallographic axes x, y and z meeting at a point O, that is the origin O. Now, let us mark the intercepts. Let distance OA equal to A, OB equals B and OC equals C. Okay. So, we have the intercepts A, B and C. Now, the angle between y and z, let it be alpha, the angle between x and y be gamma, and the angle between x and z be beta. And these are referred to as the axial angles. That is alpha, beta and gamma. So, these two entities, that is, we have the intercepts, or we may call it as unit intercepts, or it may also be called as axial intercepts, denoted as A, B and C, and the axial angles alpha, beta and gamma. These two entities characterize a unit cell. So, these two entities are together known as lattice parameters. In the previous class, we defined these parameters in terms of the elements of a crystal, right. So, here we define it in a more specific way using a more specific term called lattice parameters. Okay. So, you can see that in this figure, the plane cuts all the three crystallographic axes, and if it is a cubic cell, then we will have the structural units at the corners. Let us assume that the particles are at the corners, and you can see that this plane passes through all the three axes and through the structural units. Okay. So, the plane cuts or pass through the lattice points, and that is why these parameters are also called lattice parameters. Okay. So, we have two types of lattice parameters. We have the unit intercepts, which is A, B and C, and also the axial angles denoted by alpha, beta and gamma. So, these 6 parameters characterize a unit cell. So, we have seen what is meant by a unit cell and what is meant by a space lattice. And we saw that a unit cell is the basic building block which, when repeated in 3 dimensions, will generate a space lattice. So, now you can see a very short video on the generation of a space lattice by translations of the unit cell through integral distances along each of its edges. Class, we saw what is meant by a crystal plane, and we saw that a crystal may be regarded as made up of a set of parallel and equidistant planes which are parallel to the crystal faces and passing through the structural units, and we called them as crystal planes. Now, instead of saying a crystal plane, we can call them as lattice planes, because now we know what is meant by a lattice, what is meant by a lattice point. Okay. So, here the structural units, now where these structural units are placed? These structural units are placed on the lattice points, right. the periodic array of the lattice points generate a three-dimensional lattice. So, when a plane passes through these lattice points, such planes can be called as lattice planes. So, from now onwards, we will call such planes as lattice planes because such planes are parallel and passes through the lattice points. Let us see some examples for lattice planes. Okay, again it is a cubic crystal. Suppose we have particles at all the corners of this cube and consider a plane on the front face. Okay. So, consider this plane. You can see that the plane is passing through these lattice points or the constituent particles, and also it is parallel to two of the axes while it cuts the x-axis. Similarly, on figure B, you can see this diagonal plane. Okay, so another example for a lattice plane, again passing through the structural units. Let us mark the structural units. Okay, suppose the particles are at the corners. Okay, you can see that the plane passing through the lattice points. Okay, now consider the third one. Again, first let us draw the constituent particles. So, this plane, so this you can see that it cuts all the three crystallographic axes and passing through the lattice points. So, likewise there can be different types of lattice planes, either cutting the crystallographic axis or going parallel to some of the axes. And in the previous class, while discussing the laws of crystallography, we discussed about the law of rational indices. And according to the law of rational indices, we saw that the ratio of the intercepts of any plane of a crystal on the crystallographic axis or intersects at the crystallographic axis, it will be either unit intercepts or some simple rational number multiples of them. Okay. And we have seen that the ratio of the intercepts of any crystal plane on the crystallographic axis is given by PA is to QB is to RC, where A, B and C are the unit intercepts. And the coefficients P, Q and R are called the Weiss coefficients or Weiss indices. Okay. So, let us draw that plane to make it more clear. Okay. So, first let us draw the crystallographic axis. We have the three crystallographic axes x, y and z, and let us draw a simple unit plane or a standard plane which cuts all the three crystallographic axes. So, let it be the plane be A, B and C. Now, let the distance from O to A, that is the plane cuts the x axis, let it be A, the distance OB be B and OC be C. Okay. So, these are the unit intercepts, and the ratio of these unit intercepts are given by PA is to QB is to RC, where A, B and C are the unit intercepts, and the coefficients P, Q and R are called the Weiss coefficients or Weiss indices. For example, the Weiss indices for a plane when the intercepts along the axis are 2A, 3B and 2C. Okay. So, we have 3 axes. So, let OX, along OX let the intercept be 2A, along OY let the intercept be 3B, and along OZ the intercept be 2C. So, what will be the Weiss indices? Weiss indices will be, you have to take the coefficients of A, B and C. So, that will be 2, 3 and 2. Now, the second one, the Weiss indices of a face, if it make intercepts 2A and 3B on the x-axis and y-axis respectively and does not cut the z-axis at all. Okay. So, we have OX, the intercept is 2A, OY, the intercept is 3B, and it does not cut the z-axis. So, does not cut the z-axis means it goes parallel to the z-axis. So, the coefficient of C will be infinity. Okay. So, then what will be the Weiss indices? It will be 2, 3 and infinity. Okay. So, we can see that the Weiss coefficients here, some are whole numbers, but when we write a quantity like this, that is infinity, it is rather awkward to represent the position of a crystal plane using this infinity. So, in order to avoid such a awkward thing, we can replace the Weiss coefficients or Weiss indices by a better term, okay, and that is known as Miller indices. So, now let us see what are Miller indices. It is a set of integers which are the reciprocals of its Weiss coefficients with fractions cleared. We have seen that what are the Weiss coefficients? The Weiss coefficients are or Weiss indices are represented by the letters P, Q and R. When we represent the ratio of the intercepts as PA is to QB is to RC, the coefficients of A, B and C are called the Weiss indices or Weiss coefficients. Now, if we take the reciprocals of these Weiss indices, okay, we have to take the reciprocals. So, what will be that? That is 1 by P, 1 by Q and 1 by R. These are the reciprocals. Now, if we convert these fractions into suitable whole numbers, okay, convert fractions into whole numbers. So, that will result in a set of integers, and that set of integers are known as Miller indices. Okay. And Miller indices are generally denoted by the letters H, K and L. Okay. If we want to represent a plane using Miller indices, you can write H, K, L in parenthesis. Okay. So, this HKL, H corresponds to 1 by P, K corresponds to 1 by Q and L corresponds to 1 by R. So, this H, K and L are a set of integers which are the reciprocals of the Weiss coefficients with fractions cleared, and these set of integers are known as Miller indices. And Miller indices are named after the British scientist W.H. Miller. Now, let us see how to find out the Miller indices of a particular plane. Okay. Let us see one example. Consider a plane that makes intercepts 2a, 3b and 2c on the crystallographic axis. Okay. So, we have given the 3 intercepts. So, let OX equals 2a, OY equals 3b and OZ equals 2c. Okay. So, these are the steps for finding out the Miller indices. So, first we have to determine the Weiss coefficients or Weiss indices. So, in this, what will be the Weiss coefficients? We can see on OX it makes an intercept of 2a. So, the Weiss coefficient will be 2, and on the second axis OY it makes an intercept of 3b. So, the Weiss coefficient will be 3, and on the third one on OZ it makes intercept of 2c. So, the Weiss coefficient is 2. So, the Weiss indices are 2, 3 and 2. Now, the second step is to take their reciprocals. So, if we take the reciprocals, we have 1 by 2, 1 by 3, again we have 1 by 2. And the last step, we have to clear the fractions or convert these fractions into whole numbers. So, for that we have to multiply these fractions using a common smallest number, okay, which is divisible by the numbers on the denominator. So, we have 2 and 3 on the denominator. So, 6 will be a suitable choice because we can divide 6 by these numbers to get a whole number. Okay. So, we have 1 by 2 into 6, 1 by 3 into 6, again 1 by 2 into 6. So, we have here 3, 2, again here 3. Okay. So, we got the Miller indices as 3, 2 and 3. Okay. So, the Miller indices are 3, 2 and 3, and we can represent such a plane like this, that is write 3, 2, 3 and put a parenthesis. So, it is a 3, 2, 3 plane. Okay. And this is how we find the Miller indices of any particular plane. Okay. First, you have to determine the Weiss coefficients, then second, take their reciprocals, and third, clear fractions and convert it into whole numbers. Let us do some more examples. A plane making an intercept A on OX goes parallel to OY and OZ. Find the Miller indices of the plane. Okay. So, we have intercept A on OX. Okay. So, on OX the intercept is A, that is it is a unit intercept. So, the coefficient is 1. Okay. So, the Weiss coefficient is 1. It goes parallel to OY. When it goes parallel to OY, that means it does not cut the y axis, and when it goes parallel, the intercept B will never cut the y-axis, or it never meets the y-axis. So, the coefficient will be infinity. Now, similar is the case with OZ also, it also goes parallel to OZ. Again, the coefficient of C will also be infinity. Okay. So, what is the first step in finding the Miller indices? You have to find the Weiss coefficients or Weiss indices. So, here the Weiss indices are 1, infinity, infinity. Now, what is the second step? You have to take the reciprocals. So, if you take reciprocals, we have 1 by 1, 1 by infinity, 1 by infinity. The last step, you have to clear fractions. So, here if we clear fractions, we get 1. Now, what is 1 by infinity? 1 is divided by a very large quantity, that is infinity. So, that will tend to 0. So, we have 1, 0, 0. So, what are the Miller indices of this plane? We have the Miller indices are, it is 1, 0, 0. So, this plane can be represented as, in the brackets, 1, 0, 0, or it is a 1, 0, 0 plane. Let us see another example. A plane makes an intercept A on OX minus B on OY and goes parallel to OZ. Find the Miller indices of the plane. So, on OX, again it makes a unit intercept A. Okay. So, the coefficient is 1. Now, on OY, it is making an intercept of minus B. So, the coefficient is minus 1, and it is given that it goes parallel to OZ. That means the coefficient of C is infinity. Okay. So, as a first step, we have to find the Weiss indices. Weiss indices are given as 1, minus 1 and infinity. Now, the next step is take the reciprocals. So, we have 1 by 1, minus 1 by 1, 1 by infinity. So, if we clear the fractions, we have 1, minus 1 and 0. So, what will be the Miller indices? The Miller indices can be represented as 1, minus 1, 0. So, the plane can be represented as 1, 1, 0. Okay. Now, if we have a negative sign, then we usually represent it as using a bar over that number. Okay. So, instead of minus 1, you can represent it as 1 bar. Okay. So, the plane is 1, 1, 0, that is 1 bar 0. Now, another one, a lattice plane intercepts the 3 crystallographic axes at multiples of unit distances 3 by 2, 2 and 1. What are the Miller indices? So, it is given as the 3 intercepts are 3 by 2, 2 and 1. So, as a first step we have to find the Weiss coefficients or Weiss indices. It is directly given, that is we have 3 by 2, 2 and 1. Now, what is the next step? You have to take the reciprocals. So, the first one will be 2 by 3, the second one will be 1 by 2, the third one is 1 by 1. Okay. Now, the next step we have to clear the fractions in order to get the Miller indices. So, in order to clear the fractions, we have 2 by 3 and 1 by 2, okay, and the last one is 1. So, we have to multiply it with a common number divisible by the numbers on the denominator. So, on the denominator we have 3 and 2, okay. So, again if we multiply this using 6, we have 2 by 3 into 6, 1 by 2 into 6, and we have 1 by 1 into 6. So, 6 by 3 is 2, 6 by 2 is 3. So, we have 2 here, 2 into 2 4, here it is 3 and here it is 6. Okay. So, the Miller indices are 4, 3 and 6. Now, one more question. Calculate the Miller indices of the plane with intercepts 2a, minus 3b and 4c along the crystallographic axis. So, we have the intercepts 2a minus 3b and 4c. So, what is the first step? We have to determine the Weiss coefficients. The Weiss coefficients are 2, minus 3 and 4. Now, take the reciprocals. So, we have 1 by 2 minus 1 by 3 and 1 by 4. Now, we have to clear the fractions. So, you have to multiply by a common number, a smallest common number. So, on the denominator we have 2, 3 and 4. Okay. So, if we multiply this by 12, okay. So, 1 by 2 into 12, then minus 1 by 3 into 12, then 1 by 4 into 12. So, 12 by 2 we have 6, 12 by 3 is 4 and 12 by 4 is 3. So, what will be the Miller indices? The Miller indices are, we have 6, 4 and 3. So, here 4 we have a negative sign here, it is minus 1 by 3. So, it is minus 4. So, we can represent it as 6, 4 bar 3. Okay. So, this is how we can determine the Miller indices for any plane on a crystallographic axis. Now, let us see some assignment questions. Question 1. What is each point or the position of a particle in a crystal lattice termed as? You have given 4 options. Question 2. Which of the following is regarded as the repeatable entity of a 3D crystal structure? Question 3. How many parameters are used to characterize a unit cell? Question number 4. If a crystal plane makes intercepts 1 by 2a, 1 by 2b and c, what are the Miller indices of the plane? And the last question, a face makes intercepts 2a and 3b on the x-axis and y-axis respectively and does not cut the z-axis at all. So, what are the face indices and Miller indices of the face? So, please try to find out the answers of these questions. We will discuss the answers in the next class. So, today we had a detailed discussion on the internal structure of the crystals, namely what is meant by a unit cell, which represents the building block of the crystal, a space lattice, which is a 3-dimensional network of imaginary lines connecting the constituent particles, and what are meant by Miller indices, which are represented as the reciprocals of Weiss coefficients. In the next class, we will see a detailed discussion on different crystal systems. Thank you.